Section 1.3 Vector Equations. A vector is a list of numbers, and a column vector, or a vector itself, is a matrix with only one column. Some examples: here's the vector u, it's 3, -1, and it's a column vector, and the u is in bold print, so often you'll see vectors written with bold print. The vector v is 2, 4, and w, we have 3 entries, it's 3, 0, 5. Now some other ways you'll see it written, and this is when we write it by hand. We can write vectors as, we'll just use the vector u with kind of a half arrow on top, or you could use a normal arrow to indicate that it's a vector, or a lot of times we'll see a letter that's underlined. So those are some other ways that we indicate that we're talking about a vector. The set of all vectors with 2 entries is denoted by r squared, and a lot of times you'll see r written, I'll write it with 2 double lines and the capital R squared like that. So that's how we'll note it sometimes. 2 vectors in r squared are equal if and only if their entries are equal. So for example, these 2 vectors are not equal because the entries have to be equal and they have to be in the same location. We can add vectors together and multiply vectors by real numbers or scalars. So here's some examples. We can add these 2 vectors together, and when we do, we add the entries together in their locations. So we'll add 3 plus 2 and -1 plus 4 in this case. And then we will end up with the vector 5, 3. And that's how we add vectors. Or we can multiply by scalars. As we see here, 4 is our scalar, and we're multiplying it by the vector 3, 1. So what we do is we multiply each entry by 4, so we'll have 4 times 3, and we'll have 4 times -1, and that'll produce the vector 12, -4. At this time, we're not going to multiply 2 vectors together. We'll look at that a little bit later. Geometrically, we identify a vector AB with the point AB in the plane, or with an arrow from the origin to the point AB. So if we're looking here at a graph, we'll label our axes. We have A here and we have B here. And then this here is the point, it's the origin. It's the point 0, 0. So if we're going to draw our vector AB, we'll draw a point at the point AB and draw a line with an arrow. So this is the point AB, and that's how we would graph our vector. R squared then is the set of all points in the plane. We have a parallelogram rule for addition of 2 vectors. If u and v are represented as points in the plane, then u plus v corresponds to the 4th vertex of the parallelogram, whose other vertices are 0, or the origin, u, and v. So just a note, 0, and I'll denote it with the arrow on top. The 0 vector in this case is r squared, so we have 2 entries, and both of them are 0. In this example, we want to let u be equal to the vector 1, 3, and v is the vector 2, 1. And here we're going to see the graphs of u, v, and u plus v, and we're kind of seeing the parallelogram rule here happening. So right here is the graph of u, this vector here, and then right here is the graph of v. And then remember that the parallelogram rule said that u plus v is the 4th vertex of the parallelogram, and this would be our 0 vector, or the origin. So we made a parallelogram here, and this right here is then our fourth vertice. And so this is u plus v. And if we look at what u plus v would be if we were to do the math out, u was the vector 1, 3, and v was 2, 1. And when we add those together, we add 1 plus 2 and get 3, and we add 3 plus 1 and get 4. So the point u plus v should be 3, 4, and we see here that we're at 3 and up to 4 for our vertice for u plus v. So it does work out. This is just a minor proof of that parallelogram rule. The set of all scalar multiples of one fixed non-zero vector is a line through the origin 0, 0. For example, we're going to let u be the vector 1, 2, and we want to express the vectors u, 2u, and -3/2 on a graph. So we'll visually see that these should lie in a straight line. So we're going to graph them. First, let's find what 2u and -3/2u are. When I multiply by 2u, we're going to have 2 times the vector 1, 2, and then that will produce the vector 2, 4. And then when I do -3/2u, we've got -3/2 times my vector 1, 2, and that will produce the vector -3/2 and -3. So we want to look at what these are graphed. First, let's graph u. We're at the point 1 and up 2. So here's my point for u, and I'll draw my vector. So this was u. And then I want to graph 2u. So that was at 2, 4. So we're up here. And so if I draw it, we see we overlap u and continue on. And so then this is 2u. And now we want to graph -3/2u, and so we're going to go to -3/2, and then we're going to go down to -3. So we're about halfway through and down at -3. And we're going to draw our line from our origin down to that. And so then this is the vector -3/2u. And you see that all of these vectors lie in a straight line. So as long as they're scalar multiples of one non-zero vector, then when we graph them, they're all going to be in the same line through that origin. Vectors in R3 space, are 3 by 1 column matrices with 3 entries. So they're represented by points in 3-dimensional space. Vectors in Rn, or n space, are n by 1 column matrices with n entries. And so we would represent it this way. A vector u that's in Rn has n entries in it. So whatever u sub n would be, so our vector u that's in Rn would have n entries. So if it was, let's say R5 space, then it would have 5 entries in the column vector. And our 0 vector, we denote with 0 this way, and basically that means that just all of the entries are 0. So here are a few algebraic properties of Rn. For all vectors u, v, and w in Rn, and all scalars c and d, we have the following properties. U plus v equals v plus u. So we can change the order of addition, and it doesn't affect it. And then we can change the grouping. So parentheses u plus v plus w is equal to u plus parentheses v plus w. And then in our third property here, we can add 0 and it doesn't affect the vector. We end up with the same vector itself. And then if we add a vector plus its opposite, or the negative times that, then we will get the 0 vector. Okay, where negative u denotes -1 multiplied by that vector. When I multiply by a scalar c, essentially what I'm doing is then distributing c to both u and v. And then we do the same thing if I have c plus d, my scalars, multiplied by a vector. That vector is distributed back to both. When I multiply C parentheses du, we can group the scalars together and multiply them and then multiply by the vector. And then when I multiply by 1, I just get the vector itself. Now we're going to look at linear combinations. Here's a definition. Given vectors v1 through vp in the space Rn and given scalars c1 through cp, the vector y defined by the following equation is called a linear combination of our vectors v1 through vp using the weights c1 through cp. And here's some examples of linear combinations of v1 and v2. I can have 3v1 plus 2v2, and that is a linear combination of those two vectors. Or I could simply have 1/3 v1, and that's a linear combination of both vectors because I could write it as 1/3 v1 plus 0 v2. And so I'm multiplying v2 by the scalar 0 in this case, but it's still a linear combination of both, even though you don't visually see v2 here. Or I could have v1 minus 2v2. Or we could simply just have the 0 vector, which is always a linear combination of any number of vectors. In this case, it would be 0v1 plus 0v2. And that's a way it's a linear combination of both. Let's look at this example. We want to let v1 equal the vector 2, 1, and v2 be the vector -2, 2. We want to express each of the following vectors as a linear combination of v1 and v2. And then we're going to graph them. So first let's graph v1. It's at the point 2, 1. So here's v1. And then let's graph the point v2. We're over here at -2, 2. So this is v2. And now we want to express A, B, C, and D that were given as linear combinations of those two. So first let's graph these. A is at the point 0, 3, which is right here. And B is -4, 1, which is over here. C is the point 6, 6, so we're up here. Let's see. This was A and this was B. And then D is 7, -4. So we're going to kind of use the parallelogram rule, and we can see that A is the 4th point of my parallelogram if I was to add v1 and v2. So we see then that A is v1 plus v2. And we can check that if I add v1 and v2, 2 plus -2 is 0, and 1 plus 2 is 3. Now we see that B, if I was to flip v1 across the axis here, down to -2, then it would be the 4th vertex of these. So I'll kind of draw a dotted line here. It would be the 4th vertex of that. So what we have then for B is that it would be -v1 plus v2, or we could just say v2 minus v1. And let's double check that. If I take v2 and I subtract v1, then I have -2 minus 2, which is -4, and I have 2 minus 1, which is 1. So now let's look at C. We see that C, we're going to take v1, and you'll look at the squares here, there are 4 lengths of it to get over here, and then we have 1 length of v2. So then we have that C is equal to 4v1 plus v2. That's how we form our parallelogram, where C is that vertex of it. And let's check 4 times v1, we would have 8, 4. And when I add that to v2, 8 plus negative 2 is 6, and 4 plus 2 is 6. So that is our linear combination for C. Now let's look at D. We see that we're over here. So we would take, we have v1 plus, and then we would take v2 and flip it over, so plus or minus, and we have 1, 2 and a half. So we're going to subtract 2 and a half, or 2.5 times v2. And we can check that as well. If I have v1, which is 2, 1, and then I have negative 2.5 times v2, so I'll get 5 and negative 5. So what I have is 2 plus 5, which is 7, and 1 minus 5, which is negative 4. So that's my linear combination for D. In this example, we want to let A1 be the vector 1, 0, 3, A2 be the vector 4, 2, 14, A3 be the vector 3, 6, 10, and B be the vector negative 1, 8, negative 5. We want to determine if B is a linear combination of A1, A2, and A3. The vector B is a linear combination of A1, A2, and A3 if we can find weights x1, x2, and x3 such that the following is true. x1 times our vector A1 plus x2 times our vector A2 plus x3 times our vector A3 is equal to the vector B. Or we can rewrite that same equation substituting our actual vector in place of A1, A2, and A3. And we have this, and now we'll substitute B, which was negative 1, 8, negative 5. Then we can rewrite this as a system of 3 equations, which is this system of equations here, and all I've done is distributed x1 to each of the values in the vectors, and we get this set of 3 equations. So if I write this as an augmented matrix, we have the following, and if I use my calculator to row reduce to reduced echelon form, I get the following, which means that x1 is equal to 1, x2 is equal to negative 2, and x3 is equal to 2. So B is a linear combination of A1, A2, and A3, since we can write it as B is equal to 1 times A1 minus 2 times A2 plus 2 times A3. So let's review that last example and see exactly what we did to come up with our answer. We put our vectors A1, A2, A3, and B into the columns of an augmented matrix. And then the solution to my linear combination was found by solving that linear system whose augmented matrix was here, where our columns were A1, A2, A3, and B. So we row reduced it and found the solutions. A vector equation, given here, has the same solution set as the linear system whose augmented matrix is, given here, where the columns are simply the vectors A1 through AN and B. In particular, our vector B can be generated by a linear combination of A1 through AN if and only if there is a solution to the linear system corresponding to the augmented matrix. Let's look at this definition. Suppose V1 through Vp are vectors in Rn space. Then the span of those vectors is equal to the set of all linear combinations of V1 through Vp. Stated another way, the span of V1 through Vp is the collection of all vectors that can be written as a linear combination in this form, where x1 through xp are scalars. And the span is also called the subset of Rn spanned or generated by our vectors v1 through vp. So let's look at this example. We're going to let v be the vector 3, 4, 5. And we want to label the origin together with v, 2v, and 1.5v on this graph. So 2v is equal to the vector 6, 8, 10, and 1.5v is equal to the vector 4.5, 6, and 7.5. And when we look at the graph, right here is the origin with 3 zeros. Right here is my vector v. Here is 1.5v, and here is 2v. So we can label kind of what we've got. Since v is labeled here, then we see that this is about 3, here is 4, and this height here is 5. So v, 2v, and 1.5v all lie on the same line. And the span of v is the set of all vectors of the form CV, where C is a scalar. So here we see span of v is a line through the origin. Now let's look at this example. We want to label u, v, u plus v, and 3u plus 4v on our graph down here. So without telling you what the vectors are themselves, I'm going to just tell you that this is u and this is v. So then we would have this point here would be u plus v, and then using our parallelogram 3u, we're going to go up 3 squares here from u, and 4v, we're going to go up 4 squares here. So these are our endpoints, and this would then be the fourth endpoint. So this point up here is 3u plus 4v. So u, v, u plus v, and 3u plus 4v all lie in the same plane. So that means then that the span of u and v is the set of all vectors of the form x1 times u plus x2 times v. So here we see then that the span of u and v is equal to a plane through the origin. In this example, we're going to let v1 be equal to the vector 2, 1, and v2 be equal to the vector 4, 2. First thing we want to do is find a vector in the span of v1 and v2. Remember that the span is the set of all linear combinations of those two. So we can find any vector that's a linear combination of those. So one example would be 2v1 plus 3v2. And there's going to be multiple answers to this, but this is just one example. So if I multiply v1 by 2, then I'll have 4, 2. And if I multiply v2 by 3, then I'll have 12, 6. And then when I add those two together, I'll get the vector 16, 8. So this is just one example of a vector that is in the span of those two. Now we want to describe the span of v1 and v2 geometrically. First, we want to notice that v2 is a multiple of v1. So when that happens, then the span of v1 and v2 is a line, not a plane, but a line through the origin, our 0 vector, and our vector v1. And that happens when one vector is a multiple of the other. Now let's look at spanning sets in R3. In this first picture, we have V1 and V2, and we notice V2 is a multiple of V1, and so I'm just going to say that it's 2V1. And then we can mark this vector up here. This will be 2 times V2, which is also then 4 times V1. Or we could have written it as 2 times V1 plus V2. So V2 is a multiple of V1, and when that happens, the span of V1 and V2 is equal to the span of V1, which is also equal to the span of V2, which geometrically is a line through the origin. So now let's look at this other picture here, kind of separate us out here. We have V1 and V2, and we see that V2 is not a multiple of V1. And so this kind of, we looked at this picture before, but our point up here would be 4V1 plus 3V2. And when V2 is not a multiple of V1, then the span of V1 and V2 is equal to a plane through the origin. Here's an example that I want you guys to work on. We have V1 and V2, and I want you to determine if the span of V1 and V2 is a line or a plane. And then this next example that I want you to work on, given the matrix A and our vector B, we want to tell, is the vector B in the plane spanned by the columns of A? So it boils down to answering the question, do x1 and x2 exist so that we have this equation, x1 times our first column of our matrix A plus x2 times the second column is equal to our vector B. So you'll need to write this as an augmented matrix and then row reduce it and solve and find out if we have a consistent system or not. And we will go over your answers in class.